we have been discussing about various experimental techniques. What is the physical principle behind the experimental technique? What are its main features? And also in which class of problems these techniques could be ideally used. And we have discussed the method of caustics in the last class. And when you look at each of the techniques, there are pioneers who have made significant contribution into the development of these techniques. Professor Kalthoff from Germany was a person who has worked on caustics and made it to its perfection, and there have been contributions from Theocharis and also from Rosakis and his group at Caltech. So, many scientists have contributed to development of each of the techniques. If you look at any technique, if you look at strain gauges, if you look at holography, these are all not developed by a single individual. Someone identifies the physics behind it and the idea is initiated, then people carry on and many scientists contribute to it. And what we saw in the last class was, we had seen at the tip of a crack you have a nice caustic shadow obtained, and we explained how this shadow is formed, and we also looked at that the silver line what you have is the caustics. And in actual experimentation, you just measure this diameter, and then you have equation which will help you to find out what is the parameter associated with this problem. In this case, you will be able to find out the stress intensity factor by measuring the diameter. And I said caustic is not a general purpose experimental tool, it is only a high stress gradient problems you get information from this. And what you find here, you do not have any information in the shadow region. So, this prompted researchers to find out how to fill in information even in this zone. And if you really look at the method of coherent gradient sensor, that is what we are going to discuss next, that has originated from this aspect in mind. And what you have here is, it is a double grating lateral shearing interferometer providing whole field fringes in real time. So, we have emphasized some of these concepts. We have said whenever you look at an optical technique, you have to find out whether you get information in real time. If you get information in real time, it makes your life lot more simpler. And we have seen any technique which involves double exposure, you need to do post processing, and only then you see the fringes in real time. Whereas techniques like photoelasticity, Moire, you do see fringes in real time. On similar lines, you also find coherent gradient sensor gives you fringes in real time. And here the optics is little involved, and also the principle is also, the mathematics are quite involved. So, what we will do is we will have a bird's eye view of what this technique is. And what you find here is, you have a light, if it is opaque model, it gets reflected from the surface. If it is a transparent model, it gets transmitted, and you are really looking at the distorted wavefront. And you look at the distorted wavefront and you find out the direction cosines of the object wavefront. This is what you essentially do in the optics, and this has different meanings when I do a transmission arrangement or when I do a reflection arrangement. So, what you find here is, in a transmission arrangement, I relate these to the gradient of the sum of principal stresses. So, this is what I had said, for each of the techniques what you find here is, there is a physics is exploited, and that physics dictates what is the information you get from interpreting the fringe patterns. And here what happens, you are able to get those direction cosines related to the gradient of the sum of principal stresses. This is what happens in a transmission arrangement, and when I go to reflection arrangement, what I get this, I relate this to the gradient of the out of plane displacement. So, we have seen a very similar parallel information when we are looking at holography. What we said was, I can find out essentially out of plane displacement, and in fact, when I want to combine photoelasticity and holography, I exploit the feature of holography to measure the change in thicknesses because of Poisson ratio that is related to sums of principal stresses that we had looked at it. So, they go together when I have out of plane displacement and also its relation to in plane problems, it could be related to sigma 1 plus sigma 2. So, what we find here is I can apply coherent gradient sensor in transmission arrangement as well as reflection arrangement. In transmission arrangement, I get the gradient of the sum of principal stresses, and in reflection arrangement, I get the gradient of the out of plane displacement. I get only a gradient, I do not get actual values, I get only the slope. And what you find here is this has found wide application in dynamic studies. So, if you look at dynamic fracture, Professor Rosakis and his group and Harish Tippur, they have developed this technique. They have found it useful for dynamic fracture studies. So, what you find is in the caustic shadow you lose information. Caustics is not a general purpose experimental tool. On the other hand, coherent gradient sensor, because it gives information on the entire region, this has been used for finding out curvature. That is what we had seen in few classes earlier. We had also looked at the shearing interferometer can be used for finding out slope and curvature, and in a sense it complements the data that is given by caustics. There are also experimentalists who have combined method of caustics and method of coherent gradient sensor to be recorded in one optical arrangement. See, I have been saying if you have a problem on hand, you may not be able to solve all the quantities that you want by using one experimental technique. You may have to use multiple experimental techniques in a generic sense. I have shown that people have combined strain gauges and brittle coatings, so that they could do and solve industrial problems very quickly. And we have also seen if I want to find out separation of stresses, interferometric technique and photoelasticity could be combined. On the other hand, people also thought of recording this information simultaneously. Such equipments also have come. One is use and perform experiments separately, then process the information. And once you decide that these are the two information I want, people also devise new equipments wherein they could either simultaneously record or record one after another with the same optical arrangement with modification of what you want to insert. Such a development has also been seen in combining method of caustics and coherent gradient sensor. So, such information available in the literature. And now what we move on to do this is, but let us have a very interesting discussion on naming of experimental methods. You may wonder, name can signify many things. You know, if you look at the development of languages, if you look at Sanskrit, even for nouns they find out a root and then they explain because of such and such reason this is named like this, and it is a very well developed and scientifically, it has a grammar which is scientifically proven, and people find it easy for implementation in the computer. In fact, for natural language processing, Sanskrit grammar is so convenient, you can translate from one Indian language to another language. The intermediary is Sanskrit and then go to it. And if you look at, because we are looking at naming of experimental technique, let us also look at what way names are given in Sanskrit. I will give you one example. In Sanskrit, the sabda is very important, and the phonetic rendition of the word has some idea of what the word connotes. And if you want to talk about the tooth, the Sanskrit name for this dantam, and you will be surprised if you do not have a tooth, you cannot pronounce it. It is very interesting. You know, the why you say Sanskrit is so perfect. I am not getting into language division and things like that. When there is a positive and scientific aspect attached to a particular language, as scientists we should recognize that merit, and it is so interesting. It is dantam, you call it. I can call the tooth by several different names, and the phonetic rendition has a link to the meaning or what it connotes. So, if you are not having an understanding, then you can find out and think about it and go to the root and find out what the meaning is. So, it is not arbitrarily named. So, dantam, you pronounce it, you need tooth for it, and it is a tooth it indicates. Now, let us look at, have we named our experimental techniques scientifically. Okay. And if you look at, one of the first technique was photoelasticity, and there is a discussion, there is no unique approach to name an experimental method. And if you look at 1930s, one of the earliest optical methods that came into existence was photoelasticity. Why call it as photoelasticity? People have used optical methods to reveal the stresses. So, they have combined optics and stresses, and photography was also prevalent at that time when they were recording the information. So, they, instead of combining optics and elasticity, they called it as photoelasticity, they call it as photomechanics. And even now there is a debate, should we call it as photoelasticity or photomechanics or optomechanics. There is a school of scientists who feel we have to go and rename all the techniques, and because we are using optics, why do not we call it as optomechanics. So, if you look at photoelasticity, you have just combined the sensor, optics is used as a sensor, and you are analyzed for elastic problem. So, you call it as optoelasticity, photoelasticity. So, that is how we have named it. And when you come to strain gauges, what do you do? And this is what I caution, because people named it as strain gauges, there is a danger that you get strain tensor. It is not so, it measures only a component of strain. Because it basically measures strain, they called it as strain gauge. And if you go to strain gauge literature, you find special grid configurations where you find out the stresses. So, you call that as stress gauge, your shear stress gauge, torque gauge, likewise you name it. So, strain gauge has got its name from this. Then you have holography, and holography, it is named after what it records. And what we find here is, I have mentioned that holography records both intensity and phase of the object wavefront. Holo means whole or full, because I record both the information together. Following the example of photography, they called it as holography, and we have also seen it is a very fundamental contribution to the scientific community. So, whoever has developed the holography, he got the Nobel Prize for it. It is such a very important development. And then what you have? You also have techniques where you use the physics. I said that in the method of caustics, you employ the principle of caustics in the formation of the shadow, and you name it directly as method of caustics. And whenever you have a two grids superimposed, you get Moiré fringes seen, and you call that as Moiré. Similarly, wherever you use speckles, speckles are formed on the diffusely reflecting surface, specularly reflecting surface, you qualify the surface. And when you use those, you call those methods as speckle methods, and when we go to digital image correlation, it uses white light speckle, but you call it by a different approach. And we have also seen coating techniques. What we have seen? We have seen brittle coatings, we have seen birefringent coating. Why do I call it as brittle coating? I have a coat that is put on the model, it fails in a brittle fashion. In fact, when brittle coating was originally developed, they were all used for finding out plastic deformation, and when you have a rolled steel, you have scales that are formed. So, they flake like a brittle coat. So, they were able to identify zones of plastic deformation. That is how the whole technique developed. So, you name the technique based on how the coating behaves. I said photoelastic coating, other name of photoelastic coating is birefringent coating. And I said in photoelasticity, the physics used is temporary or artificial birefringence, and that is what is exhibited by this coating. So, you call it as photoelastic coating as well as birefringent coating. And we have also have another technique, thermoelastic stress analysis, and I cautioned you again and again, do not misconstrue that this technique can measure stresses due to thermoelasticity. It is not so. The physical principle used employs measurement of temperature, which is very small, and you call this as a thermoelastic stress analysis. So, it is based on the physical principle, and I said I have one of the emerging techniques now is digital image correlation. It uses white light speckles, however, this is named after the method of data processing. I have digital images and then I look at undeformed and deformed configuration and then do a correlation. So, I call this as digital image correlation. So, techniques are named differently. I do not have a unique approach, and if somebody wants to develop a new technique, he coins what is more appropriate. And what you see in coherent gradient sensor, why the technique is called coherent gradient sensor. If you look at that, I use a coherent source of light. It is essentially a sharing interferometer. By combining the nature of light source and the type of information it can provide, the technique is named. And you know researchers also want attention to their work. So, one of the reasons why they coin a technique is to attract the attention of others to look at what this technique is all about. So, coherent gradient sensor is very famously known as CGS, which is essentially a sharing interferometer. Now, people call it as sharing interferometer. That is how they, because it has become a general purpose analysis tool, people do it for thin wafers. In when you go for MEMS application, thin wafers are analyzed for out of plane displacement, slope, curvature. So, you have this. So, I combine the type of radiation that I use, I have a coherent source of light and I measure the gradient. So, I call it as a coherent gradient sensor. Next, we move on to a very important aspect which we have also seen and discussed a little bit earlier. What we looked at was in most of the optical techniques you get fringe patterns, and we need to understand certain issues about how these fringe patterns are. First, what I need to do is I need to find out whether the interpretation what I do for the fringes is acceptable or not. A simple exercise is compare it with an analytical solution. If the comparison is correct, then you understand that this is what the technique gives. The other approach is look at the physics of the problem, find out what all the physics can reveal, then come and link that this is what the technique is capable of giving. And what we find in the case of beam underbending, we have looked at the central portion and then we said we will plot contours of sigma 1 minus sigma 2. The analytical solution turned out to be horizontal lines. When I look at the experiment, what happens? I get this as horizontal lines, but they are not thin lines. I have a band, but nevertheless I got horizontal contours. And we said why you see that as a band is because of the limitations of the recording medium, one observes a fringe contour as a band. And all optical techniques you will see only a band. And one of the most challenging and difficult aspect for any experimental analysis is how to go and number these fringes, because I need to know the fringe order, then I need to use the appropriate equation and find out what is it that I will have to interpret on. And what you find here, instead of a monochromatic light source, if I view these patterns in a white light source, I get not black and white contours, but contours with color, contours with distinctive color, and this is the specific advantage of photoelasticity. So, what I could do is, by knowing the color, it is possible for you to find out the fringe order. It is also easy for you to identify how the gradient information changes, whether it is increasing in this direction or decreasing in this direction. You can find out whether the color sequence is repeating in a particular fashion. Whether the color sequence repeats in a particular fashion, then you can identify positive gradient and negative gradient, all that you can find out. So, one of the most challenging aspect is quantitative extraction of data from all these experimental techniques. But the focus of our attention now is to find out richness of qualitative information that you could get from fringe patterns, because this gives you a sense of comfort in looking at and interpreting the fringe patterns. Let us look at what we have seen is fringe is a band, we have seen it, and mere record of the fringe patterns itself can provide useful qualitative information. So, we have to look at what all the qualitative information that you could identify. One of the things what you could see is I get it as a band, and if you look the fringe patterns closely, are the bands of uniform thickness. The thickness of the band is inversely related to the gradient or the variable it represents. So, that we will see, I have a fringe pattern from photoelasticity, because photoelasticity has information in color, a colored fringe pattern is taken, and I also have a fringe pattern in Moire, and what we will have is we will have a closer look at how the fringe thickness varies, and this just shows that for you to draw your attention, you have these fringe patterns drawn earlier, go back and then look at that fringe contour is not of same thickness, the thickness changes, and that is what is tried to be shown in this slide, and you have a very broad fringe here. And let me repeat, I have very sharp fringes here, and the same fringe becomes increasing in thickness. So, essentially what you find is that fringe band is not of constant thickness, and I mentioned in one of the classes you have this fringe plotting by a software, when you have to go and mimic what is the way to get the fringe band. One of the information you use it variation in the variable, even if you give a constant variation in the variable, because the gradient changes, automatically the thickness of the fringes changes. When the gradient is small, fringe is very broad, when the gradient is very high, fringe is very sharp. So, I can find out by looking at the fringe patterns whether the gradient of the information is high or low. I can find out from the thickness, and this is not a property of photoelastic fringes. You see a similar one even in moire. I go to moire and then look at it, you see this is a very sharp, thickness increases, and that is how you find. And same fringe has thick and thin, it is thinner here, it is thicker at the corner, and this becomes much thicker. So, when you look at the fringe pattern, observe for all these indirect information. The fringe pattern speaks to you, this is how the distribution is. So, take note of it. Suppose I have fringes closely packed, then I would say that this is the zone of high stress concentration. Later on I can go and do a technique, do a quantitative processing and try to get the actual data, that is a different issue. But the moment you look at a fringe pattern, you should react to it. You should know that this is stress concentration region, and this is the region where I can scoop out material. I need to get that kind of information, and you get that by looking at the thickness of the band, as simple as that. So, this is one of the qualitative information you get. Then what is the other information that you can think of? I have said that density of fringe contours indicate that the value of the variable it represents is quite high in that zone. Suppose I want to compare two different designs, and the ideal way is take the fringe pattern for both the cases and compare the fringe pattern and find out based on qualitative appreciation how you can evaluate the different design. So, it is used as an optical comparator, and one simple example is given, and what you find here is I have a example of two different type of spanners, and in one case I have given this as a streamline fillet. Let us understand what is the idea here, and you all have you are all mechanical engineers. So, you know how a fillet is made. How a fillet is made? Suppose I go to any machining process, it is easier to make a circular fillet, because the machining operation is simple. I can go and make a circular fillet, and why do I make a fillet? I would like to minimize the sharp geometric changes, and then I would like to have a smooth variation, and this smooth variation you could do by a fillet. So, you essentially reduce the stress concentration. And if you look at forging operations or casting operations, when you look at forging or casting, I do not have the restriction of having only a circular fillet. I am not doing a machining. In a machining operation, circular fillet simplifies your fabrication of the component. When I go for casting and forging, I have the luxury of choosing any type of fillet I want. Non-circular fillets are more common in those applications. And how do they arrive at such odd shaped fillets? And you have an example here, and what you find here, I have this contour like this, and I can also enlarge it further, and what you find here, the fringes are many in this zone, they are not tangential to the boundary. I would like you to make a sketch of it. I would like you to make a sketch of it, and this is an example problem that is shown. I have one circular fillet here, I have another circular fillet here, I have another circular fillet here, they are not joined, so you do not have a smooth transition here, and when I make a spanner out of it, I find in this zone the fringes are not tangential to the boundary, and you focus only on this region, you do not have to focus on the other regions. Make a neat sketch of, bring out that the fringes are not tangential. So, when you have a fringe pattern, you have to look at very closely and try to extract as much information as possible. And obviously, I have a load application point, I have fringes originate here. So, it also indicates a stress concentration zone, and what I find here is, as such, when you see only one design, you will only see, oh, these colors are good, the fringes are good, that is the way you will interpret. Only when you see a counter example, you will find that the knowledge is different. Now, what I will do is, I will go and show the other one, then come back to this, okay, so that you will know what is the difference. Now, I take this example, and what I find here, the contour is, the fillet is smooth, it is non-circular here, and you find more or less these fringes are tangential to the boundary, it merges with the boundary, it merges with the boundary of this, and these are called streamline fillets. So, only when you see the difference, you will know what is the advantage, and they are very strong, they are very strong. You need to concentrate only on the, do not worry about the nut, you concentrate only on this region where I am showing the arrow, you need to worry about the fringes. You find the fringes are parallel to the boundary, by and large there is some small aberration is there here, but compared to the earlier one, here the fringes are lot more smoother and parallel to the boundary. And in fact, when people design some of those castings and forgings, they take a photoelastic model which is slightly large in shape, and then keep on shaving the material until for the given loading you get the fringe tangential to the boundary. In fact, there is a famous book by Haywood, Designing by Photoelasticity, where he talks about how to get a streamline fillet. And when you get a streamline fillet, the component will have very high strength, nothing happens to the component, and I can afford to have a streamline fillet which is not always circular in a forging and casting, there is no problem. And you know, these spanners are done by forging, so I can afford to have a non-circular fillet and take advantage of our understanding of stress distribution. So, let us see these fringe pattern one after another. I see this as tangential to the boundary, and I go back and then show the other one, you will find that this is different, and this is a fictitious example, you know, you do not have a spanner like this is done to illustrate. I have a combination of circular fillets here. So, when I do is, I have lot of deviation from this, and this is not strong, you can have failure initiated in this, and in service it can fail. So, what you do is, I do not do a quantitative analysis, even a simple qualitative exercise can help you to improve your design. So, this is another aspect of richness of qualitative information. Okay. In a production line, you know, I would like to inspect whether my component is being manufactured correctly or not. I can have a optical comparator, and what we are going to look at is insertion of a bush in a circular hole. This is what we are going to look at as an example. So, what we are going to look at is how fringe patterns helps you to check the quality of the finished product. What I am going to do in a quality checking mode, I will accept or reject based on some evaluation of fringe patterns. And I have example here, I have one example where I have a perfectly circular bush inserted in an annular plate, and you all know Lamy's problem, you need to get concentric fringes, I do get concentric fringes. And this is not what happens in an actual production line. In an actual production line, if you do not maintain the cylindricity of the bush, you can have surprises like this. And what I see here, I see extra flowery pattern, and let us look at little more closely here. So, what I have here is I have bush is cylindrical, you can go and accept the component, and while you sketch it, what you do is you do not have to draw all these fringes, you say essentially they are concentric. And when I have a non-circular bush which has undulations which are not visible to the naked eye, but when I insert, I get this flowery patterns on the inner boundary. I have inserted a bush in a circular hole, it should behave like a Lamy's problem, concentric circles I should get, but instead what I get is I get fringe pattern like this, and in this case the deviation is quite obvious. It is very striking, the fringe pattern what I find is very striking. I can quickly say something has gone wrong. If the variations are very subtle, then I cannot make a judgment. In fact, one of the most difficult thing is if you have a member and stretch it. Invariably, if the member is not stretched correctly, you will always have some amount of bending, and if you take a specimen which can respond optically, any small misalignment will show up in the optical fringe pattern. So, experiments, simple experiments are really very difficult to conduct, even a simple tension. So, one of the ideas what they suggest is if you have a situation where you need to verify the alignment, go for optical techniques and improve your alignment based on that. So, optical elements are very good, they are very sensitive to any one of this loading peculiarities, and what we see here, you have concentric fringes and you have the fringes which are coming as a flower, and that is what you have. I want you to make a reasonable sketch to bring out these difference, that is the idea. You have a flowery pattern and you have a concentric circle, and that gives you an idea that something has gone wrong, and you can take corrective action. You can go and modify your production line, inspect the how the product is made, go and improve the process parameters. So, you can take some kind of corrective action. So, now you realize that by looking at mere fringe patterns, we have extracted quite a bit of data. We can find out stress concentration zone, we can compare different designs, we can also accept or reject a component based on some of this information. So, that is quite useful. I mean, we have been able to take note of this. And another advantage what you have is, I have a defect here. What I have is I have a plate with a hole and I have a coating put on this, and here I have taken example. So, I know that there is a hole present, and now I am interpreting that you have a hole that is seen in the fringe pattern. In fact, to find out internal flaws, people have attempted putting a photoelastic coating, and when the model is loaded, the fringe signature can identify presence of flaws in the member. So, this is another approach, people have used it, and identifying a flaw in a structure is a very challenging aspect. And what is the difference between an ultrasonic technique? In an ultrasonic technique, even benign flaws will be detected, because it will only look at material separation. On the other hand, if I have a technique where the model is loaded, those flaws which are sensitive, which can pose problem to you, only those will be revealed. See, collecting lot of information is not necessary, you need pertinent information for a given problem. So, this is one of the reasons they cite, if you use an acoustic emission technique, you are searching a needle in a haystack, because you get so much information, identifying your pertinent information is extremely difficult. So, on the other hand, if I have a technique which can reveal those flaws which are going to give you problem alone will be detected is well and good. And I have also emphasized in one of the classes that people also have looked at all these fringe patterns as piece of art. In fact, Professor Durelli has made significant contributions in looking at fringe patterns like this. So, my interest is all of you please just note down some of these reference details. You do not have to write the full reference. He has a paper in applied mechanics, developments in theoretical and applied mechanics in 1970. This maybe you may not be in a position to get it, but at least the experimental mechanics you will be able to get it. So, you write down this experimental mechanics and write the page numbers and the year. You do not have to write the title of the article, you can easily search it based on the reference. There is another paper in experimental mechanics on art, science, beauty and the experimentalist. So, people have written not one paper, 3 papers he has written and variety of fringe patterns he has shown. And it is very interesting because when you are looking at optical techniques, you should also look at the other side of it. There is beauty attached to it, lot of qualitative information that you can get out of it. So, what you need is you need to have some of these references. You should not just focus only on your stress analysis, you should also know related information that makes your learning lot more enjoyable and purposeful. So, this is very interesting, that is why I thought that I should show you this. And now, let us look at key technologies that have influenced experimental mechanics. Obviously, invention of lasers gave a boost to interferometric techniques. I said when holography was invented, Dennis Gaber had only mercury arc lamp. So, he could not take the advantage of technology. The moment lasers came into picture, all our interferometric techniques have become refined, they are lot more sensitive and you could go for long phase difference calculation. Once you have lasers, you also had development of pulse lasers. So, you have intermittent illumination, you could extend conventional methodologies to record dynamic phenomena, and dynamic phenomena recording reveals lot of interesting information. See, if you go and have water that is getting boiled, it looks as if it is random, it is not really random. You have bubbles formed at periodic intervals and come out and then they burst, and people do research on how this bubble formation, so on and so forth. And recording dynamic phenomena, like you have a microscope which optically magnifies, you have a time magnification here. You are able to record at very minute intervals and see it as a slow motion film, you understand the physics behind it better. Stress waves in solids were revealed beautifully by photoelasticity. Until then people were not understanding what are stress waves. When you see the fringe pattern, when you see the fringe patterns move, that gives lot of understanding on the phenomena. And you need, if the process is very fast, then I need ultra fast recording. And one of the issues in ultra fast recording is I should have a light source which is strong enough to illuminate, because when I have a long exposure, I am not worried about the intensity of light. Even a dim lit condition, if I have long exposure, I can record. When I want to record a dynamic phenomena, there has to be a perfect match between your amount of light available and the shortest time that you want to record. So, they go together, and pulse lasers are very intense and you could achieve some of these advantages. So, what you find here is pulse lasers have helped in recording dynamic phenomena. Then what you have right now, you have very sleek equipment, and fiber optics has done the trick. I can have a light source and take the light where you want through the fiber and then go into your elimination. In hazardous environment where I cannot go near and do it, suppose I want to test a pressure vessel, I can't go near the pressure vessel and test it, I have to stay away after a barrier, and I want an elimination, I can have a fiber optics to do that. And you have plenty of laser printers around, they all use diode lasers. So, whatever the technological development that influences the way that you do the experiments. So, what you find is the availability of fiber optics and diode lasers has influenced the growth of commercial equipments suited to industrial environments. You want some kind of robustness and you would like to have, and this is possible with such developments. And all the optical techniques, if you really look at the development of image processing, earlier they had used a lathe bed on which they will put a photograph, and then you will on the tool post they will have a optical sensor which will pick out the information, and the whole thing will traverse, and that is how they digitized. Digitization itself may take several hours. Then you go to the computer and do extraction of features, other things people have done. Now you have charge coupled device cameras, you instantly get the digitized information. So, all optical techniques now replace human eye. No one does in the field inspecting the component with a human eye, you have electronic eye which records this information, then you process it. So, it has provided a fundamental shift because I can record intensity data. So, I can have new ways of data processing possible. So, this is the particularly the influence of technology, but for the technology you could not think in this direction at all, and for all optical techniques people use phase shifting methods. And parallelly you also had development in manufacturing, you have what is known as rapid prototyping, and this has significantly reduced the lead time in fabricating a prototype. And fortunately, one of the rapid prototyping technology known as stereolithography uses certain kind of resin which are also photoelastically sensitive. And I had told you earlier in 1930s when people were devising different components, they have all gone through mandatory 3-dimensional photoelastic analysis. So, one of the challenge in photoelastic analysis was fabricate a 3-dimensional model, and now with rapid prototyping fabrication has become lot more simpler. Not only it is lot more simpler, I have a CAD model to fabricate the prototype, the same CAD model can be used for finite element analysis, the same CAD model could also be used for photoelastic analysis, because I fabricate the model, I do the slicing, and then I am able to bridge numerical analysis and experimental analysis. That way I will have more confidence in solving complex problems. And what you find here is technology has a very important role to play, and you have to absorb technology. That experimental techniques will survive only when it is open to development of technology and absorbs those aspects. If you stay away from computer processing, no experimental technique is going to be useful. So, what we have looked at in this class was, we have started with a brief look at what caustics were. Then I said in the caustic shadow you do not get information. So, you have coherent gradient sensor which provides information in that shadow. Then we moved on and looked at briefly how to name an experimental technique, some discussion on why a particular technique is given a particular name, so on and so forth. Then we looked at a reasonable extent on how the qualitative information of fringe pattern can provide useful information. See, in an industry people want answers yesterday, When they come to you for a problem, they want the answer so fast. So, you will have to use your engineering judgment and do detailed analysis only when it is required. So, even if you are able to make certain judgment based on qualitative inputs, it can go a long way in solving your problem on hand. Then finally, we looked at technologies have played a very significant role, and we have looked at how interferometric techniques got a boost from lasers, and we will see in the next class how material research. See, if you look at any scientific advancement, it is the invention of new materials that contribute to it, and what we would look at is in which way experimental mechanics has gained because of material research. Every advancement of science, if you look at heart valves, it has a root from your space technology. They had titanium based alloys which had which are also found to be biocompatible. That is how percolates. When you do high tech research, it percolates down to human suffering alleviation. So, we will see material research development, how it has helped experimental mechanics in the next class.